Hi, this is Nastanovsky. We're going on with this mini course on self-referential paradoxes. So this is section 3.4 of this book called The Outer Limits, this book called Monoidal Category Theory. And so today we're going to finish up those self-referential paradoxes. Okay, it's a lot of material, but the main thing is it's the same theme over and over and over. Okay, and because it's the same theme over and over and over, it gets a little bit easier. Okay, so we're going to do two broad things today. We're going to do Turing's halting problem, which shows that there's no way to tell if a computer will go into an infinite loop or not. Okay, and then we're going to do fixed points in logic, and we're going to have Gödel's incompleteness theorem and other types of things like that, and then we'll finish off with a little bit more of a discussion. So let's talk about Turing. So Alan Turing, in the 1930s, he's considered the father of computer science. Before engineers created computers, Alan Turing figured out what computers cannot do. Okay, and so he gave different examples of things that computers cannot do. One of them is called the printing problem, but what's attributed to him, although it came a little bit later, is something called the halting problem, and we're going to deal with that. Okay, and so the halting problem asks as follows. He says, given a program, and given an input to that program, and we're going to talk only about programs that accept natural numbers and output natural numbers, okay? Or we don't care what it outputs, but it accepts a natural number. Okay, so given a program that accepts a natural number, tell me, given this program and this number, and you plug it in, does it go on to an infinite loop, or does it halt? Does it stop? Okay? Now, I said this before, but let's say it again. Every single program can be thought of as a natural number, and already there you have self-reference. Okay, because let's see what's going on. You have programs that deal with natural numbers. Okay, and those programs have natural numbers. So you're going to have programs dealing with programs. Another way to think of it is you have numbers that represent programs which deal with numbers, and so you have numbers dealing with programs which deal with numbers, so you have numbers dealing with numbers. Okay, self-reference. Now, it's not strange for a computer scientist to see this self-reference or to see computers dealing with computers. Operating systems are programs that run other programs, or programs that run programs. So we have this self-reference. You need it. It's a necessity of all computers, and what we're doing here is we're dealing with that. Okay, hold on. Okay, very good. So let's deal with the following. So what does the halting problem want? It wants a function like this. Okay. It should accept two numbers. Okay, so let's write it like this. Sorry. Let's write it like this. Halt takes two numbers and outputs a bool. And a bool, by a bool I mean 0 or 1. Okay? But I'm thinking of this in the categories of computable functions. Okay? So yes, there is a function that says, oh, a program will halt on input n, or something like that. Yes, there is a function. Okay. The question is, can we write a program for this function? Can we determine this function? So this map takes place in the category of computable functions. Okay, let's just remember what the category of computable functions is. The objects are types, like natural numbers and bool, and the morphisms are functions that have computers. Okay, so great. This is going to be equal to 1 or 0 if input m in program m n halts. Okay, and this is if input m in program n goes into an infinite loop. Okay? Okay. Again, this function exists. We want to know, can we write a program that does it? Okay? Let me just give away the answer. The answer is absolutely not. It can't be done. Okay. Okay. And the proof is exactly the same way as every other proof that we saw before. So let's do it. You ready? I need some room here. Okay, I'm sorry, it's a slightly, I mean, it's the same, you'll see it's the same picture, it's a slightly different. Let's assume that this program, halt, is computable. Okay, so it means that there is, within the category of computable functions, there is a nice thing called halt here, okay, and it goes to bool. Okay, great. Now, you've seen this before. Okay, that's the diagonal function. Okay, and you know what I'm going to write over here. Bool is 0 or 1. I'm going to write it over here too. Okay, and I'm going to complete this. So this was analogous to what we saw before. We called this F, and we called this G. Hold on, I'm not going to call it G. I'm going to call it something else in a second, but I also don't want to, I want to change this. This is not. Don't write that down. It's not, okay? Not switches 0 for 1, 1 for 0. Here, I want another function, okay? I want a function that doesn't switch 0 for 1 and 1 for 0, okay? Because I'm trying to get self-reference, okay? And what we want to know is, does the program halt or does the program go into an infinite loop? And I want to negate that answer. So instead of saying yeses become nos, trues become falses, and falses become trues, I want to do it as follows. So this is going to be called par for partial not. Okay, let me show you what that is. Okay, partial not, let's do it over here. Partial not, okay, it accepts 0 or 1. So we're going to write that as n, okay, and it outputs, well, what do we want? If it outputs a halt, if it does halt, which means a 1, okay, so if it does not halt, I want it to halt. So we do this. Sorry. It's a 1 if n equals 0, which means what? If it doesn't halt, I want this to halt. Say 1 is halt, 0, okay. As opposed to that, if n is not well, it's Boolean, so it's either 0 or 1. So if it's not 0, what is it? It's 1. Then I want it to, not 0, but I want it to go into an infinite loop. Okay? And it's very easy to write a program that goes into an infinite loop. You just say, go to this line, and this line just goes to itself over and over and over, forever and ever. The main point is, I want to negate what was done. So we're asking a question, does it halt, does it stop, or does it go into an infinite loop? And I want to switch the answers, and so I want it to go into an infinite loop or say that it halts. Okay, so that's this partial function. Main point is, this is not a total function. Sometimes it doesn't give, it just goes into an infinite loop. Sometimes it gives an answer, sometimes it doesn't. Okay, great. Now, I want to call this function, simply following the other computer literature, I want to call this halt n. Okay, halt prime n. Okay, let's just see what this does. Let's see what this characterizes in some sense. So let's just go through it. Halt prime of n. Okay, when does it output a 1? equals 1, okay, if halt, let's see, n goes here, this is going to be n cross n, and then we get this. So this is going to be a 1, okay, if halt of n comma n equals 0. Okay, let's see what that happens. So what that means is, this is going to describe those programs that halt, this is going to describe those numbers, okay, it's describing numbers, a subset of numbers, those numbers that when you plug that number into itself, it will not halt. Okay, so this is, you've seen this a million times already. It's those villagers who don't cut themselves. It's those words that don't describe themselves. It's adjectives. It's those sets that don't contain themselves. It's those, well, do Cantor's things, okay, that it's not in the surjection, etc., etc. So it's the same type of thing, okay? And the question is as follows. Is this halt prime a computable function? Okay, so what are we asking there? Is this halt prime, is there a program that runs halt prime? Okay, so let's see what would happen. So let's assume there is. So there is some number, we're going to call it n0. Okay, think of the barber, okay? So this is the program that accepts numbers, okay, that accepts numbers, and it's going to, okay, this is going to be the program that accepts numbers, okay, and it's going to tell, oh, this number, if you plugged it into yourself, it will be a 0. The answer will be 0. It will, if you plug this number into the program of the same number, it will give you, it will go into an infinite loop. Okay, so again, we're asking the same question. Can halt prime be represented by halt? Another way to say that is, can halt prime describe the numbers that are that halt prime describes? Is there some program like that does this? Okay. Okay, and if the answer is yes, what does that mean? Well, it's true for all n. So then we can ask the following question. Maybe this should be a 0. Oh, that's fine. That's fine. Okay, so then we can ask the following question. If this is true for any n, how about if we plug in the program itself into that? Okay. And so we'd get the following. Halt prime on n0 is equal to 1 if halt prime of n0 comma n0 is equal to 1. However, how was halt prime defined? Okay, and this means that halt prime of n0 is defined by doing this. This is equal to n0 comma n0. That's this guy. Halt, that's this guy, of par naught. Okay, that's the way it was defined. So don't tell me that this number represents this function, because if it was true, then it would be true for all n0, but here it's equal to 1. Oh, so this would be par naught. Okay, so the main point is, it would swap. If this is 0, if this is 1, this would be 0. Okay, so 1 over here gives you 1 over here, and here would be not 0, it would go into an infinite loop. Okay, you'll see this in a second when we talk about the matrix way of looking at this. It's a little bit more clearly. Main point is, this function does not have an n0. It's false. There is no way of representing it. What does that mean? Well, that means, okay, that means halt prime, there's no program in the world that can do halt prime. Okay, so again, what are we doing? We're saying a function is not representable by this halt, which means that the function cannot be written as a program which accepts inputs. Okay, so and gives the answer. So there's no program that does halt prime. We'll see this in a second again. Okay, but what does that mean about halt? Just because halt prime doesn't exist, what does that mean about halt? Well, let's look at what halt says. This is definitely computable. Okay? This is definitely computable. Okay? Because I can always write a program that outputs double of it itself. This we assumed computable. This, I can write a program that does this. So this is computable, this is computable, okay? If this is computable, then the composition of three computable functions is computable. You can always tag functions along, tag computer programs one after the other and get computable functions. Okay, so again, this is computable, this is computable. If you assume this is computable, this is computable. Uh-oh, we prove that this is not computable. Conclusion, this is not computable. Okay. Okay. If you assume this is computable, you get that this is computable, okay? But this is not computable, therefore this is not computable. Okay, so this program is not computable. And that's it. So Turing's halting problem is not a computable program. There's no way you're going to write a total computer program that does this. Okay, let's do it in terms of the matrix because it's easier to see. Okay, so let's do it as follows. This is the halt program. Okay, and again, the inputs that you can have, so let's write this as inputs. Okay, and this is the programs. So the inputs are 0, 1, 2, 3, 4, 5, 6, ... Okay, and the programs are program number 0, program number 1, program number 2, program number 3, program number 4, program number 5, program number 6, program number 7, ... Okay, and now halt is supposed to output a 0 or 1, and this could be a lot of different zeros or 1s. So 0, 1, 1, 1, 0, 1, 0, 1, 1, 0, 1, 0, 1, 1, 1, 1. Okay, ... This is 0, 1, 1, 0, 1, 1, 0, 1, ... Okay, this program always outputs a 1, no matter, always halts. Okay, we should have one that always goes into an infinite loop. Okay, fine. This one is, let's say, a 0. This one is, let's say, a 1. This one is, let's say, a 1. This one is, let's say, a 0. Okay, fill it up with all zeros and ones. Okay, assume this is a computable function. Very nice. Okay, and now what are we going to do? We're going to look at input 0 with program 0, input 1 with program 1, input 2 with program 2, input 3 with program 3. Okay, so we're looking along this diagonal. Okay, that's the self-reference you get. Okay. This red line, this red function, it accepts natural numbers and gives out yes, no, if it halts or doesn't halt. Okay, so now we have a little bit of change of scenery here. Instead of this is 0, that means it does not halt. We're going to make it into a 1, which means it halts. Instead of this being a 0, we're going to make it into a 1. Here's the interesting one. Okay, this says program 2 on input 2 will halt. Well, I don't want it to halt. I want to give the opposite answer. I want to give it the opposite answer. And so what I want is that this should be, this should be up arrow. Okay, this should be 1. This should be up arrow. This should be up arrow. This should be 1. Dot, dot, dot. Okay? Okay, so this is halt prime. That's what this diagonal is, okay? And now we ask the following question. You ready? Question is very simple. Question: is there any program 0, 1, 2, 3, 4 that does the same thing as halt prime? Let's go through that again. Is there any program that does the same thing as halt prime? Okay, so we're asking, is there any n0 over here? And the answer is absolutely not. Why? Because it's different than this program right over here. This program is going to output a 0 here, and we're going to want an output of 1. It's different than this program because this program is going to output. It's different than the second one because here it's going to output a 1, okay, and this is going to output. This is going to go into an infinite loop, etc., etc., etc. Keep on going. So every single column is going to be different than the diagonal. Conclusion: the diagonal is not. The diagonal is not any program. And if the program doesn't exist, if halt prime doesn't exist, then you know what? Halt doesn't exist either. Okay? Because we constructed halt prime from computable functions, from things we thought were computable functions, and the fact that it doesn't work shows that halt is not a computable function. Okay, great. That takes care of that. I just would like to read it as a self-referential statement. Hold on. And basically, it's on page 129. Okay, what does halt prime really say? The fact that halt prime doesn't work on n0, so I just erased it. If you, it's all these self-referential statements are making a statement about themselves. For example, the barber is the person who shaves everyone and doesn't shave themselves. The set R is the set of all. The set R is the set of all. I'm sorry. The set R is the set of all sets that do not contain themselves. The word heterological describes all adjectives that do not describe themselves. Okay, etc., etc. So what does this halt prime do? Okay, and the answer is it does the following. If you ask whether a program will halt or go into an infinite loop, if you ask whether this program, so halt prime on n0, if you ask whether this program will halt or go into an infinite loop, then this program will give you the wrong answer. Okay, that's swapping it. Okay, that's swapping of 1 to 0, 0 to up arrow, etc. That's giving the wrong answer. Okay. Computers cannot give the wrong answer. Okay, computers give the exact answer that they're programmed to do. Okay, but what we're doing is by switching these, we're giving the wrong answer. We're giving the different answer than what it's supposed to be giving. And let me just say, since computers cannot give the wrong answer, halt prime cannot exist, and so halt cannot exist either. Okay, so that explains Turing's halting problem. Okay, great. So that takes care of a lot of those are a lot of consequences of Levier's theorem, which he calls Cantor's theorem, and does that. Now, Levier's theorem is extremely important. Cantor's theorem is very important, okay? And the way we want to see it in many different ways, okay? Because we want to understand it from many different aspects, okay? So what I want to do now is look at the same theorem, but from the contrapositive point of view. Contrapositive, just for those of you who don't remember, this is P implies Q is the same thing as not Q implies not P. That's the contrapositive. If it's raining, then there are clouds in the sky. If there are no clouds in the sky, then it's not raining. Okay? If you go more than 50 miles an hour, you will get a ticket. If you did not get a ticket, that means you did not go more than 50 miles an hour. Okay? So that's the same thing. So that's what the contrapositive is. So what I'd like to do is, I'd like to restate Cantor's theorem in a shortened version, and then do the contrapositive of it. Okay, because we'll have of Cantor's theorem. Okay, so what does Cantor's theorem say? It said, given a category A, given a product, given a terminal object, okay, those are the things we needed, okay, given a Y, given Y is where we had those output values, and given an alpha from Y to Y. Okay, all this was given. Okay, then we had the following statement. Ready? Let's restate that. Every F from A cross A to Y has, let's restate it. Okay, it says as follows: if alpha does not have fixed points, that implies, okay, so let's leave out this if. Alpha does not have a fixed point means every F from A cross A to Y has a G from A to Y that is not representable. Okay, that's Cantor's theorem. Okay, and we saw okay, so if it has fixed points, then every F has a G, and we saw as G is not representable. What's the contrapositive? It's the same thing. Given a category A up with products and a terminal object, and Y an object, and alpha from Y to Y, something that messes things up. Okay, so now we're going to say the contrapositive of this. So what's the contrapositive? If every F from A cross A to Y has every G from A to Y is representable. Okay, so this says every F has a G that's not, but if every F has every G is representable, then alpha has, not that it does not have fixed points, alpha does have fixed points. Okay, so that's the contrapositive. Okay, what we're going to do here is we're going to get, I'm going to apply this, we're going to get contrapositive, we're going to get fixed points of logical systems. Okay, so let me explain to you what that's all about. Okay. Okay, let me explain to you what that is. So first of all, we need some lingo. So we're going to talk about logic. So we're going to have A is a sentence. That means it's either true or false. B is a sentence. C is a sentence. D is a sentence. These are logical sentences. Okay? And we're also going to talk about predicates. Okay, and predicates we're going to write with script A and script B and script C. Good Lord. Okay. script C and script D and script E, etc., etc. These are predicates. These are statements that take X, a number, okay, and output yes or no, true or false. In other words, they depend on what X is. Okay? Okay, so these are predicates. So again, these are statements that are either true or false, and these are statements that depend on an input and a true or false. And we're dealing with systems that are complicated enough to deal with natural numbers. Okay, so that's an important thing. So we're going to be able to manipulate natural numbers and deal with them like that. Okay, one more thing. I'm sorry, many more things. Okay, we're not just dealing with the set of sentences. We're not just dealing with the set of predicates. What we're dealing with is what's called the Lindenbaum classes. Okay, of sentences. I'll explain to you what it is in a second. And the Lindenbaum classes of predicates. Okay, this is called, it's a category, Lind sub 0. That means it takes 0 inputs, or Lind of 1. That means it takes 1 input. Okay, so what's a Lindenbaum class? Well, it's not just the things, but certain things will be logically equivalent to this. So B is not the same sentence as C, but they're logically equivalent. In other words, this one is true and this one is false. This one is true. They're just two ways of saying the same thing. Same thing here. You're going to have D is logically equivalent to A. That's a script A. I'm sorry. Okay, what that means is when you plug in numbers here, you're going to get things that are logically equivalent. Okay, so we're not just dealing with A sentences, we're dealing with whole classes of sentences, okay, that are logically equivalent, okay? And that's going to be very important when we're dealing with fixed points, because what we're going to do is we're going to say one thing is going to be equal to another thing. So that's what a fixed point is. Alpha of, I don't know, x is equal to y, okay? Well, a fixed point is alpha of x is equal to x. That's what a fixed point is. But in terms of numbers, if you're dealing with just numbers, that means it's the identity on x. But what we're going to be able to do is we're going to have alpha of d is going to equal to a. Here, if these are logically equivalent, even though this statement is one statement, here's another statement, but because they're logically equivalent, it's like it's a fixed point. Okay, it's a fixed point in the Lindenbaum classes. Okay, so for example, let's just say with it. Today is Tuesday is logically equivalent to tomorrow is Wednesday. Okay, those are logically equivalent. Here, you ready? X is happy and handsome is logically equivalent to X is handsome and happy. Okay, so X is handsome and X is happy. Whatever. The point is, those are trivial examples of, with commutativity, where two statements, different statements, are really equal. So we're going to have that. Okay. 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 Now, sentences and equivalence classes of sentences and predicates, they're all made out of symbols, okay? And symbols, just like computer programs can be a number, symbols can also be made into a number, okay? And so you're going to have, let's say, a sentence C, and you could talk about the number of sentence C. Okay, you're going to talk about a predicate A, and you're going to talk about the number of predicate A. Okay, now, what does that help? Well, and I did this 10 minutes ago when we talked about programs acting on programs, so we're going to do the same thing here. If A deals with a number, X is a number, and then you can find a number that deals with that, so then you can talk about one predicate dealing with another predicate. So for example, we could have this. Okay, so this predicate is dealing with the number of this predicate. So just like you can have programs dealing with programs, so too you can have predicates dealing with predicates. And again, let's just say it in another way of talking about it. Okay, you can have a number which represents a predicate, okay, being plugged into a predicate, and you get out. And so you have numbers talking about numbers, you have predicates talking about predicates, you have all types of fun and exciting things. Okay, great. Okay, so now I want to talk about fixed points of logical statements. Hold on. I want to look at this contrapositive from the matrix point of view, because it's going to be very, very helpful. Okay, and the idea is as follows. We always have these matrices, and we fill in the things like this. Okay, and then what we do is we change the diagonal. Okay, so whatever's on the diagonal, I don't want to be exact here, okay? Whatever's on the diagonal, what do? Well, we do alpha of it, okay? And we change it, 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 okay? Okay, and great. Now, this whole thing, remember this matrix we call F, and this whole thing we call G. And what was our main point? Okay, we did this a million times. What was our main point? Main point was G by this alpha was different than this row, and different than this, and different than this, and different than this, and different than this, and different than this. Okay, we made G to be different using this alpha. Great. Okay, and what that means is that if we had another row, if we had some row, okay, we'll call it, I don't know, maybe N0, okay? Actually, these things should be left open because they go on forever and ever, okay? The main point is that this, don't say that G is represented by any N0, because it's different. How is it different? It's different right over there. Okay, that's where the difference is. Great. So that's the statement in its regular form. Now we're going to take the statement in the contrapositive form. What's the contrapositive form? It says as follows. It says as follows. For any F, G will be represented. Okay, G will be represented if F is complicated enough, or if with a system that you're dealing with is that it will be represented by something, then what does that say? That this diagonal will be represented by this. Okay, so what this gives you is two different ways of talking about things. This way, and we're going to see this, okay? And you know what? The very fact, so what this shows is this is a fixed point, and so this point is going to be called something N0, F of N0, comma N0, okay, and what do we have? On the one hand, it's just F of N0. This is the N0 row. I'm sorry, this is the N0 row in the N0 position. So we have F of N0, comma N0. Okay, that's that point. But on the other hand, we had changed this because it's on the diagonal. So we have this. How did we get this? This is alpha of f of 1 comma 1, and this is alpha of f of n of 2 comma 2, etc., etc. So on the other hand, we have this. Alpha, what's this? It's the same thing as alpha of f of n0 comma n0. Okay, and that's a fixed point. I'm sorry, that's a fixed point. Okay, so let's restate the contrapositive. Let's restate the contrapositive, and we'll do it. Ready? We're going to restate the contrapositive and say as follows. Okay, if there is a function and every diagonal does equal something, is equal to, can be represented by a certain column. If there's a diagonal and the diagonal can be represented by a certain column, bingo, then we have a fixed point on that thing. Okay, and so that's the contrapositive. Let's say it again. If there's no fixed points, then there's something that can't be represented. If everything can be represented, then there are fixed points. Okay. Okay, great. We're going to use this fixed point machine right now. So let's show it. Okay. So the idea is as follows. We're going to have predicate x. Okay. And basically a predicate x is you plug in a number and it's going to tell you something about that number. Now, you can plug in any number you want. In particular, you plug in a number. I'm sorry, this is a predicate, it depends on x. But if you plug in the number, for example, if you plug in the number 53, well, then that statement is either true or false. That is a true or false statement. Okay? That's a true or false statement. So that's a predicate, that's a sentence. Okay? Another way to look at this is E of, if that's a sentence, if A is a sentence, that's the number of a sentence, okay? E of the number of a sentence is a sentence that's either true or false. Okay, so now we have, I'm sorry, so let's do this again. A is a sentence. The number of the sentence is a number. E of a number, E is a predicate. You plug in a number, you get a true or false statement. And so you get that. Okay, now what we're going to do is create something called the fixed point machine. Okay, what's the fixed point machine? It says as follows, given any predicate, okay, I'm going to be able to find a sentence, C, that's going to be equivalent to E on the sentence C. Okay? Okay, now that's a hard thing, but let's just see what it means. What it means is, what C basically says is, and again, by the way, this is equivalent, logically equivalent. So this is one sentence, this is another sentence, but they're logically equivalent. What C basically says is, hello, what C basically says is, this sentence has property E. Okay? So it's talking about itself. Here, E is talking about the predicate A sentence A has the property E. Here we're saying C says it has its own property. Okay? So it has its own sentence. Now, I'm sorry, C says this property has it's very hard. Sorry, C says that the number of the sentence C has property E. So that's very hard. So it's a sentence talking about itself. Hence self-reference. That's all we've been talking about for the past 2.5 hours. Okay, so this sentence has property E. I just want to show you why this is very hard, because take property E, okay, and you find some sentence and you plug it in. I don't know, call it D, okay? Well, that could be equal to some other sentence, but you know, it probably is equal to sentence K or something like that. Okay, so in order to get this fixed point, but that's not what you want. This says, sentence K says that sentence D has property E. I don't want that. I want sentence C to say the number of sentence C has property E. So it should talk about itself. This K is talking about some other sentence, which is fine. Okay, so the way to do this is you have to do both of these at the same time. You have to somehow work with both of these at the same time, and we will do this, okay? And I just want to tell you kind of where it is. We were dealing with the diagonal, and we were dealing with a column, okay? And so that's where this sentence is going to be. The fact that you have to do both of these, this is going to be part of the diagonal. I should have made it in red ink, and this will be part of the rows. And the main point is, at some point, they're going to be fixed. They're going to be touching each other. Okay, now this fixed point machine is what we're going to use to get all the logical phenomena that we're talking about. And we will do it. I will describe this fixed point machine, but it's a little bit complicated. And rather than losing people, this is not like a book. I do it in the book at this point, but in the book you can just turn the pages and get it and skip over it. And I say skip it because it's the first time you read it, it's a little bit hard. But in a video, I want to do it, and I'll do it in 10 minutes at the end. Okay, we'll come back to this and show you how the contrapositive of Cantor's theorem gives you this fixed point machine. Okay. For now, just assume that we have this fixed point machine, and let's see how it works. Okay. So the first example, which is the most famous example and the most important example of all these self-referential things, is something called Gödel's incompleteness theorem. Okay, this is a very important and very famous theorem. Okay, and it goes as follows. Not only can we make a number, by the way, this is all Gödel's doing, not only can we make a number, not only can we make a sentence and a predicate be a number, okay, but a sentence and a predicate, we can prove properties about these numbers. We can look at the number, decompose it, figure out what the sentence is, and then find out properties of it. Okay, and not only are we going to say a sentence has a number, not only are we going to say a predicate has a number, but we're going to have many sentences and many predicates, and they're going to form proofs. What's proofs? Proofs are exact statements, one after the other, where one thing follows each other. Okay, and so you can make proofs into a number. So again, proofs are a series of sentences, and each one of them has a number, and then you can take those and you can make numbers. This is what Gödel's paper is all about. It's a lot of technical details, but we people who use computers have no problem with this, because we know that sentences and paragraphs, they can all be saved as bits, and we know that they can all be made into numbers. And you know what computers do? Computers take those numbers and they take the numbers and they get out the sentences. Okay, so what Godel was doing, something in the 30s, we now do all the time. We save things as numbers, we get it back as the original thing, lossless transfers. Okay, Gödel's incompleteness. Okay, so there is a predicate called prove. Okay, and takes two numbers. Okay, one is y. This is a proof. This is a number that represents a proof, and this is a number that represents a statement. Okay, and the main point is, if you take this number and you take this number, you can decompose these numbers and you can say what the proof is, and you can say what the statement is, and you can actually check that proof and see, does it actually prove it? Okay, so you're dealing with some axiom system, you're dealing with some logical system where you know exactly what you're allowed to use, what axioms you're allowed to use, how you derive one thing from the other thing, etc., etc. You know the rules of the system, and you can program those rules of the systems, or you can write mathematical formulas that describe those systems, and you get out a nice predicate like this. And so this will equal to true or false, okay, depending if the formula that y describes, so we'll write that as y, proves x. And it's false if y does not prove x. Okay, main point, this is a number, and then we get a true or false statement. Okay, great. Not interested in this formula, I'm interested in this formula. For all y, it is false. Okay, so that's a statement in logic for all y. We're going to see more of that later. That's a quantifier. It's just a way of saying it. Any possible number, it is false that prove, I did it without the e, okay, prove of y comma x. What does that mean? Okay, this is a logical statement. The y is bound here. Okay, so there's only, so this is a logical predicate. It only depends on x. Okay, and basically what it says is the statement that's in x, okay, is not proved by anything. Okay, any number that represents a proof does not prove, it does not prove x. Okay, so what this says is x is unprovable. The statement that's represented by x is unprovable. Okay, great. So let's make a predicate like that. Okay, e of x is equal to, e of x is equal to, it's a statement that says no matter what input, no matter what attempted proof, it's not a proof. No matter what number, that number is not a proof of x. In other words, x has no proof. X has no proof. Okay, great. Good. Now, that is a totally legitimate legal sentence. It's a totally legitimate legal predicate. Okay? It is a legal predicate. You can put it in, and you can actually do this. You can ask whether, you can plug in a number, and you can tell true or false whether it's there. Okay, but now what happens next? I'm going to take this and I'm going to plug it into the fixed point machine. Okay, and so I'm going to get a formula C, which is going to be equivalent to e of x. Okay, which says, sorry, I didn't do the fixed point machine, okay, which is going to be equivalent to the number of C. Okay, so that's an amazing thing. Now we're having the predicate, the sentence talk about itself. And basically, this sentence will have the E thing. This sentence will have the E property. I don't want to call it E, I want to call it G for Godel, because Godel was the one who came up with the sentence. Okay, I just have to say, Godel did not really prove it this way. He proved it in a much more complicated way. This was proved by Carnap a few years later, and but you can see it's the same type of proof as we're going to see. It's the same type of proof as Cantor's theorem. It's the same. It's Lever's theorem. Okay, and what does G say? What does the number of G say? It says, ready? For all y. Give me any number whatsoever, it is false that proof of y, comma, not C, G. Okay, now, this says that x is unprovable. Now, G says G is unprovable. That's exactly this. G says G is unprovable. So this says, this sentence is unprovable. Okay. Okay, great. Now we want to ask the following question. Is G provable? Okay. Well, if G is provable, then the system is flawed. Okay? Because what does it say? It says, G, here's a proof of the sentence that says I'm unprovable. If you prove G, if there's some, I don't know, y prime, such that proof of y comma G, if you can prove that, then you're proving a sentence which says you don't exist. There's no such y prime. Okay? So that means you're proving something that it says it doesn't exist. So there's something wrong with your system. Okay? Either you didn't plug in the right rules of it, or there's something wrong with it, or you're proving statements that you know is false. Okay? So answer, if G is provable, then the system is flawed. Fine. Okay? If G is not provable, okay, then the statement is true. Okay, then the statement's true. Okay, that's the core of the argument. That's an amazing argument. Okay, so if it's not true, well, that's an exact. If it's not provable, well, that's what it says. It's not provable. Conclusion: it's true, because it says it's not provable. Therefore, it's true. Okay, so let me just give you like a historical background to why Gödel's incompleteness theorem is so shocking and so important. And I'll say it's one of the most important theorems of the 20th century. Okay, and I don't say that lightly. Okay, before Gödel came along, people thought, well, I'm not sure what people, but people thought whatever is true is provable. Okay. Came along Gödel and he said, no, watch out, that's not really true. There's true things, and then there's a subset of that called provable things. Okay? And then he said, the reason why he said this is because he has this G statement over here, which is true, but not provable. Okay? And so there are statements in mathematics that are true but not provable. That's an amazing thing. And again, all this is totally logical, systematic, exact formulas, etc., etc. So that's Gödel's incompleteness there. And again, it's a very important statement. Okay. Let's do another one of them. This is called Tarski's theorem. And there's all types of history of this. This came out after Gödel's incompleteness theorem by Tarski, but Gödel claimed that he saw this already and he knew it, and it's a little bit simpler to say. And maybe he did. Okay, so Tarski's theorem says as follows. Okay, Tarski's theorem says as follows. He says, well, you could tell a lot of things. Given a number x, okay, and let's say x corresponds to some sentence A, okay, well, you could tell a lot of things about the sentence A by looking at it. You can look at whether it's a proof. You can look at lots of things. You can look at how many letters it has. In other words, you could take the number x, decompose it, get back A, and you could tell a lot of things about it. And he says as follows. He said, can you make a predicate T and say whether or not, let's say, true or false, 0 or 1, okay, if, I don't know, X is true, if X is false. Okay, so again, we saw that you can take a number which corresponds to a sentence or a sentence or a predicate or a proof, and you can tell lots of different properties about it. Okay, great. Question: can you tell whether or not the statement is true within this logical system? Okay, that's a legitimate question. And he said as follows. Tarski said as follows. He says, if you can, then you can make the following predicate. Okay, E of X is equal to, E of X is equal to not T of X. Okay, well, in that case, if you can do this, if you can make a logical sentence like this, then you can make this logical sentence, which basically says the number X is a number of a statement that's not true. We're getting something close here, something that we do. Okay, so we have such a legitimate predicate. Again, assuming T is a legitimate predicate, then we can do the negation of that, and then we can ask the following. Let's put it through our fixed point machine. And then we get a sentence, C, okay, such that C is E of C, okay, which is equal to, it's false, okay, okay, and basically C says that C is not true. Okay, but we know this sentence a long time ago. We've seen the sentence a long time ago. What's this? This is basically the liar paradox. This is a sentence that says I am false. Okay, this sentence says I am false. Okay, now, is it true or false? Let's go through it. If it's true, then what? If C is true, then what does it say? It says it's false. It's false that it's true. That C, the number that corresponds to C, is false. Okay. If it's false, then it's false that it's false like that, and so it's true. So true implies false. False implies true. You get a contradiction in your logical system. Okay. It's flawed. Your logical system will be flawed. Okay. And the answer is no. You made an assumption here. The assumption was that T was describable. You're not allowed to do that. It's not. You cannot describe, looking at the numbers, you cannot tell whether something is true or false. Okay, so that's Tarski's theorem. So, and again, it's a beautiful theorem. Okay, let's talk about another one. Okay, and this is called Parikh sentences. Okay, now what's this about? Okay, well, not only can you tell whether or not something is provable or not provable, you can also tell about the length of the proof. Okay, and so we get the following sentence. Okay, so we get the following predicate. This is a predicate. It has a subscript n because it's important. The n is important. Okay, it takes a number and tells you something about that number, and basically it says as follows. You ready? It is false that there exists an m less than n, such that proof length of m comma x parentheses. Okay. Let's see what it means. So proof length means true or false. Is there a proof of length m again, you can see how many characters this proof has, how many little symbols it has. Is there a proof of length m that says x is true? Okay, so now let's look at this whole thing. It says E of n as a predicate depends on x and n, okay, and it says of x. So we want to know about the x. X is some sentence, okay, and basically it says it's false that there is a proof of length less than n. There's a proof of length m which is less than n, such that it's true, such that m that there's a proof of length m that has x. Okay, let's write down what it means in English. X is a number of a proof, of a sentence, X is a number of a sentence that does not have a proof of length less than n, period. X is a number of a sentence that does not have a proof of length less than n. Okay, it does not have a proof of a, okay, great. Now what do? We plug it into the fixed point machine, and we get C sub n, which is equal to epsilon, equivalent to epsilon, E of n of C sub n, okay, which basically says, let's write it out again, it is false that there exists an m less than n with proof length m comma c. Close. Okay, what does C said? C of n says this sentence does not have a proof less than n. Okay, so it's like a variation of Gödel's incompleteness theorem. Gödel's incompleteness theorem says, I do not have a proof. This says, I didn't say I don't have a proof. I don't have a proof less than n. Okay? And you can prove amazing things with this. Professor Rohit Parikh proved this in 1971 in a paper called Existence and Feasibility in Arithmetic. And in it, he goes and he talks about how you can prove sentences like this. Okay? They are provable, but you take a big enough n, you'll see that it doesn't have a short proof. Okay, but this is an amazing result. It doesn't have a short proof, but it has a proof that it's provable. Okay, so you won't be able to prove it, but it has a proof, it has a short proof that you can prove it. That's a very strange thing. Okay, so mind-boggling things in there. Okay. There's a few more stuff mentioned in the book on this that's worth doing. Okay, so those were 3 times that we used the fixed point machine. Let's just go through it. So this fixed point machine says, you're given a predicate, you can make a sentence that describes that predicate, that has that property. Okay, let's go through that again. What's the fixed point machine? Given a predicate, you can find a sentence that has that predicate. Okay, it has that value. Okay. And so we did it for Gödel's incompleteness theorem, we did it for the Tarski's theorem, we did it for Parikh sentences. And there's a ton of other things that are found in many logic books. Okay, I want to talk about 2 other things. Okay, finish with the fixed point machine. I want to talk about 2 other things before we go back and prove the fixed point machine. Okay, one I spoke about it before, there's Epimenidies and the liar paradox. Okay, let's just remember about Epimenides. He lived on Crete, and he said this. He basically said all Cretans are liars, including him. Okay, and what that's about is it's an English sentence talking about an English sentence and negating it. Okay, saying it's not true. Okay, so we can also, the liar paradox is an English sentence that says this is false. Okay, great. Now we can start doing this in the Cantor theorem, just like before. So we have a set called sentences, and we might have a function called that takes sentences cross sentences, okay, to the set 2, and basically f of S1, that's one sentence, comma, S2, that's another sentence, is equal to 1 or 0 if, okay, S1 is negated, I'm sorry, that should be affirmed, although I think I said it in the book also. Okay. That's a mistake. Affirmed by S2. Okay. If S1 is not affirmed, in other words, it doesn't agree, by S2. Okay, so far we're just following along very nicely. We're going to get to Cantor's theorem again, and then we could do something like this. Okay, and we could talk about sentences, and we can diagonalize and talk about sentences cross sentences. And we can talk about to, and we can talk about not, our old friend not, and we talk about this. This is F, okay, and we get G, okay, and G of S is equal to 1 if S negates, that's the opposite of affirm, negates S, okay, if it says something false about itself. Okay, if it says, so this sentence is a lie, this sentence is not true, this sentence is false, all those things are doing it. Okay, Epimenidies' sentence saying all Cretans are liars, knowing that he's from Crete, means that sentence is negating itself. Okay, the problem is that we have to stop here, because we can't talk about what does it mean, that's horrible. Okay, what does it mean for something to represent another thing? So the beautiful theorem of Cantor's theorem, we have to stop here because we don't have the way of talking about what does it mean to represent it. So is there a sentence that describes all self-negating sentences? Now how about this? S0 is equal to all sentences. No, this is a. It's not a sentence. That's just, I'm just making a list of them. Okay, this sentence negates all of them. You see, you don't have that. So you get partially to Cantor's theorem, but you don't really get that. Okay, now let's talk about one other topic, and that's called time travel paradoxes. Let's talk about time travel paradoxes. Okay, and so this is the famous bachelor grandfather paradox, where you go back in time and you kill your bachelor grandfather. Okay, and there's a lot of versions of this. You can go back in time. So this is the movie Back to the Future, where you go back in time and you make sure your parents don't meet or they don't get married or something like that. Okay. Now, in all these things, what you're doing is you're having, if you kill your bachelor grandfather, It's not only is it wrong to kill your bachelor grandfather, but you're not able to kill your bachelor grandfather. If you go back in time and kill your bachelor grandfather, then your father won't be born, and you won't be born, and you won't be able to go back in time to kill your bachelor grandfather. And that's a big problem. Okay? So the idea is as follows. By the way, you don't have to do that, be so brutal and kill anybody, okay? If you were able to go back in time, here's what you do. You go back a minute earlier, okay? So you open up your time machine, think of Doctor Who, you go in, you close the time machine, you press the buttons to go back 1 minute earlier. Okay, that's all you have to do. Stay in the same place, go back 1 minute earlier. Now, when you go back, you press transfer, you go back 1 minute earlier. What's happening 1 minute earlier? Your earlier version is trying to go back in, open the door of the time machine and go in. All you have to do is hold that door closed. You, who is 1 minute later, who did the time traveling already, hold the door closed. Now think about what you're doing. By holding the door closed, you are stopping an earlier version of yourself to go in and go back a minute earlier, okay? And what you're doing is you're stopping yourself from holding the door back, because if you're not in there to hold the door back, you won't be able to do it. So again, you have this self-reference. Okay, the idea is as follows. Every event affects another event. So if I let go of the pen will fall. I let go of the pen falls, okay? But with time travel paradoxes, you have events affecting themselves, okay? And when you have events affecting themselves, you get into trouble. Okay, so let's try to make this into the same type of Cantor theorem. So you have the set of physical events. Okay, there's a set of all physical events. Okay, and this is a very important set. Physicists spend their whole life studying this event, this set. Okay, and then you have events. Okay, and you have a function f, which goes to, let's say, the function 2. Okay, and how's it defined? F of e comma e prime is equal to 1 or 0 if e is, I'm going to say affirmed again, affirmed by e prime, or I should say not negatively affected, okay, if e is not affirmed, okay, by e prime. Okay, great. Well, guess what we do? You know the drill by now. This goes here, this is the diagonal, we get there, we get 2 here, this is g. Okay, and what's g? G of e is equal to 1 if e negatively affects itself. So, shooting your bachelor grandfather will negatively affect itself. Holding the door to the machine, to the time machine, will negatively affect itself. Getting your mother not to marry your father before you're born will make sure that you cannot get your mother to not marry your father before you were born. Okay? Shooting your bachelor grandfather will make sure that you do not shoot your bachelor grandfather. Okay? All these events negatively affect. Okay, problem is, events don't describe other events. So I cannot talk about what it means for G to be represented by anything. So yes, it has a feel of self-reference, it has the feel of Cantor's theorem, but it's missing out on that. Okay, so now I want to go back, finish. So that's the end of the conversation, and self-referential paradoxes are a big thing. You have to look up in the book all the references. Levere's paper. I wrote a paper where I have 19 instances of this self-reference all over mathematics and computer science and stuff like that. 19 different instances of this, so you can see it in a lot of different ways. And I revisited it in my other book on theoretical computer science for the working category theorists. I go back and I talk about instances of this self-referential things, just talking about complexity theory and incomputability theory. So we did Turing's result, but there's a lot of other results with this self-reference stuff. So it shows up all over. Okay, it's a fascinating topic. Okay, great. But now I want to erase the board, and then I want to talk about, go back and show how the contrapositive of Cantor's theorem gives you this fixed point machine. Okay. Okay, so we have to prove this fixed point machine theorem. So let's talk about the category. We're talking about the category of sets. Okay, okay, and we have Lindenbaum 1. Let's remember what this is. This is the set of equivalence classes of predicates. Okay, and we have Lindenbaum 0. That's a set of equivalence classes of sentences. Okay, great. And now we're going to have a function, which goes like this. And like everything else, we've done this a million times, we're going to call it f. Great. Okay, now I got to tell you how it's defined. Now that's a very strange function. It's going to take a predicate, and it's going to output a sentence. Okay, well, what's this all about? It's about things. It's about things describing each other. Okay, so logic can describe logic. So we have sentences describing sentences. We have villagers getting cut by villagers. We have sets containing sets. We're going to have logical sentences, predicates describing predicates. So we have as follows. You ready? This is going to be a typical predicate, A. This is going to be a typical predicate, B. Okay, and where should it go by f? Ready? It should go to the following. B like that. Okay, let's go through this. This is a predicate, this is a predicate, this is the predicate, this is the number of the predicate, and B does this. So let's go through this. This is true, this sentence is, it's a sentence, it's either true or false. It's true if A has the property that B is describing. If the number of A has the property that B is describing. So this is a yes or no answer. Okay? That's a legitimate answer. Main point, this is a sentence. It has no variables. This is a number, and you plug it in, and you get out a true or false sentence. Okay, so that's very nice. We've seen that before, and we've seen, so what did we have here? Let's just think. We had adjectives describing adjectives. We had villagers cutting villagers' hair. We had sets containing sets, etc., etc. So we have logical predicates having logical predicates. Okay, great. Now that we have f, let's do, you know the diagram I'm going to make now. Lind 1 goes to here with this diagonal. Okay, and this was alpha. We're going to have to fix that in a second. Okay, this will go to Lind 0. Okay, and we're going to get a function like this, g. Okay, now we have to concentrate on what this alpha is. It takes a sentence and outputs a sentence. And the idea is as follows. You ready? E is some predicate. Okay. E is some predicate. You're going to plug in the number, and the number is either going to work or not work. Very nice. Okay, and so this alpha is going to depend on E. Okay, let me show you how it's defined. alpha on E of some sentence here. Let's call the sentence A, not script A, okay, is going to equal to E of A. So what does it say? Take the sentence A, look at its number, and tell whether the predicate has that number or not. Okay, I'm sorry, whether that number has that property, yes or no. Okay, and again, this E is a predicate, belongs in line 1, okay, but when you plug in a number, you get out a sentence. So we get that. Okay, great. Let's work this through. How is G defined? So G, okay, let's take a typical element in here and let's follow it around. So G of A of X, that's a predicate in here, okay, is going to equal to, follow it around, alpha E of F of doubling this. So this is script A of X, comma, script A of X. Okay, close the F parentheses, close the alpha parentheses. Hold on, we're not finished. We're gonna describe what that is. Okay, because we know how this F is defined. So let's do it. This is equal to alpha sub E, we'll fix that later, of script A of, now we're going to apply, this is going to be applied to this, but it's applying to itself. It's applying to itself. Beforehand, when I was writing B, I had A and B. Now we're having A and A. That's self-reference given by the delta. So this is this of script A of X. Script A. Close. Okay, let's just make sure, first of all, we have to get the parentheses right. Okay, let's just make sure what we have here. Okay, A of X is a predicate, the number is a number, this gives you a sentence. So this is in here, and now we do alpha of that. And what's that? Very nice. So this is a sentence, and so this becomes E of, and what do? We did it right here. Take the number take the sentence that's inside, put it in the numbers, and you get this. So this becomes the number of A of the number of A, script A, of X. X. Like that. Okay, we got to put in close. So this closes like this, and this closes like this. Okay, so basically, that's a funny thing. So basically what that does, G is those things which have the property that E is talking about when A is applied to itself. Let's go through that again. G is those sentences that has the property when A applies to itself. Very good. Now, ask yourself the following question. And this we've done a million times. We're going to ask, is G represented by something? Okay, namely, can we somehow figure out which one, what G does, how G gives you this? Okay, and the answer is yes, it is. So this is, again, the contrapositive of Cantor's theorem. Many times we had where it said, no, it's not represented. Now we are saying, yes, it is represented. Okay, okay, so I need room. Okay. And I got to tell you how it's represented. So we're going to have the following. Ready? G of A, script A, oops, there, of X. No, that doesn't get a number. Okay, is going to equal to, what does it mean represented? That means, I'll leave that there. That's F of A of X. Okay? Okay? Is there some miracle formula that does this? Is there some miracle formula that's going to take this and give out the same sentence when you plug it in? Okay? And the answer is, of course there is. There is, because logic can do a lot of amazing things. In particular, it can take the number and double itself, just like this doubles itself in some sense. So there's going to do that. So there's going to be a logical formula, G, and I go through it in the book, and it's going to accept a number. Okay? And let me just show you what it is. Okay? G. By the way, there should be like a little E here because the G depends on the E. Put it there. Okay, and that's equal to, I'm sorry, that's the same G as this, so I don't want to use that. I want to use a capital script G. Okay, capital script G of X. Okay, and what that does is it's equal to E of D of X. Okay, and what D of X does is it doubles it like this. It's a doubling function. Okay, main point. Okay, yes, this small g is represented by something, and because it's represented by something, okay, you get out. Because it's represented by something, you get out that fixed point, okay? And so the fixed point's there. I just want to finish off by pointing you to this formula. Don't move. Okay, I showed you this beforehand. This is how you get the fixed point, and then later on here, I actually do it with the formula, and so here's your fixed point, and you get it. Now, it's complicated to get to the fixed point, and the point is, you have to work hard to do it, because you have to worry about these doubling. You're having things talk about themselves, so you have to double it. Okay, main point, okay? Every f, okay, I'm sorry, given this alpha, every f can be represented by this g. In other words, you can always do it. Conclusion, you're going to have some fixed point. Conclusion, when you're talking about logical sentences, you can get the logical sentences to talk about themselves. Conclusion, you have a fixed point machine. Anyways, this is a fascinating topic. Logic is a fascinating topic. Self-referential sentences is a fascinating topic. The fact that this is all done over and over. I've spent the past 3.5 hours just doing this one little theorem over and over and seeing it all in these same places. That's absolutely fascinating to me. Okay? Okay, we are now finished chapter 3, which is about structures within categories, and now we go to chapter 4, where the real magic begins, okay? Because the whole purpose of category theory, the whole shocking thing of category theory, is not what's going on in one category, but how categories relate to each other. And so that's chapter 4, where we start talking about functors between categories and special types of functors and different types of functors over and over, and what they're all about. Okay? Okay, I look forward to seeing you. If you have any comments or criticism or something about the videos, please send me an email. Okay, ways of improving, ways of fixing, or any comments whatsoever about the book or the videos. Thank you. Let me know.